Okay, we're continuing on in section 14.7, and I'm calling this part 2. It is not on exam 2, and it is the start of the exam 3 material. So here we're going to talk about finding absolute extrema. We just briefly introduced the idea that when we find relative max and mins, then when you have the one which is the most extreme, or the one that's the greatest, then it would be the absolute maximum. If it's the least overall out of all the relative or local minimums, then it would be the absolute. So we have this idea, but actually finding them takes a lot of work, it turns out. So let's start out in similar ways we did in the first part of this section, and let's see what we did in Calc 1, because it's going to be similar, but it's going to be more complicated. So here we have y equals x to the fourth minus 4x cubed. This is actually the exact same function that I used to introduce 14.7 part 1. But it's a little different now because I'm restricting the domain between negative 2 and 4 for the x. And so notice that we have some endpoints here this time. And so this is actually what we covered first when we had Calc 1 with our textbook. And so we talked about this extreme value theorem. If f is continuous on a closed interval from a to b, then f attains an absolute maximum value f of c and an absolute minimum value f of d at some number c and d on a to b, where a and b is a closed interval. It turns out that closed interval is super important here, that if we have that closed interval, then we're guaranteed to have the absolute extrema. Again here, one of the conditions was that it's continuous on that closed interval. And that's what we got going on here. So clearly we can see what the absolute maximum and minimums are. It's going to happen at negative 2 for our x, and it's going to happen at 3 for our minimum. So we can see that easily from the graph, but if you don't have the graph, and then it's a bunch of work to figure that out, but we will be guaranteed to find those. So here's something called the closed interval method, and so this is actually finding it algebraically. So here's what you do. First you find the values of f at the critical numbers of f on the open interval a to b. So this is actually exactly what we did in the first part of 14.7. So we're familiar with that. Step 2, find the values of f at the endpoints of the interval. Okay, we didn't do that in the first part, but it's really easy to do. We're given the endpoints, in this case negative 2 to 4, and we just plug those in to figure out what the y value is so that we can see how high it is, I guess, or how low. And then finally, step 3, the largest values from steps 1 and 2 are the absolute maximum value or values. The smallest in the y are the absolute minimums or minimum. So usually you only just have one, but you can have ties, and you would report all of them if they were tied. So actually doing that for this example, we already did this derivative, but just quickly doing that derivative again for x to the fourth minus 4x cubed, we get 4x cubed minus 12x squared. Notice that you can factor that and get the critical values as x equals 0 and x equals 3. And so something a little different here is that you do need to see, are those on my closed interval that I care about in this one? And the answer is yes, both 0 and 3 are on negative 2 to 4. Otherwise, they just don't apply to your problem. And so now, different thing is finding the y coordinates for the critical value and the endpoints. So the endpoints are negative 2 and 4. We got the critical values of 0 and 3. And so this next part is we're just going to go ahead, maybe handy to make a table and figure out what the y values are that go with those x values that are important. These are our candidates for the absolute max and mins. So once we do that, we just see which one is the lowest. Well, clearly negative 9 is the lowest y value here, and that occurs at x equals 3. So we can see that on the graph as the winner for the absolute minimum. And then we got our winner for the absolute maximum being attained at 48 for the y, and that occurs when x equals negative 2, which is an endpoint. So that's all a review of Calc 1. Good to have that fresh in your head, because now it's going to get more complicated, but it has the same general idea. So here we go. In multivariate, we also have an extreme value theorem. If f is continuous on a closed bounded set D in R2, then f attains an absolute maximum value f of x sub 1, x sub 1, y sub 1, and an absolute minimum value f of x sub 2, y sub 2 at some points in D. So notice how similar that is to the extreme value theorem when we were just having x values be the input or the independent variable. So pretty much the same type of thing. A few things here. D, big D, we just talked about big D in the context of it having a subscript that was a vector, which was a unit vector, and that's not the same capital D here, which is a little confusing, but here we're talking about domain, and that's why it's called D. It's a set, and usually we use capital letters for sets, and they're using D here because it's standing for the domain in terms of x and y. So just to be clear that those are different things. And so before that was kind of really trivial when we talked about the domain or the closed interval from, in our example above, -2 to 3, or was it 4? I forget. Anyway, it was just given and it's like, okay, yeah, not a big deal. But here we're in R2, so we need to talk about just briefly what it means to be a closed bounded set D in R sub 2. So first of all, again, we're talking about x's and y's together, and just some examples here can get more complicated than this, but graphically a closed set means that the border has to be solid. Notice in the sets that are not closed image, all of these have a dotted line or open point somewhere. And so if that's the case, then we just say the whole thing's not closed. The extreme case here is we got a circle that has a solid bounded border except at one point. And then that one point just screws the whole thing up, and now it's just open. We say it's open. So some more examples here. Closed set. Here would be a bounded circle centered at the origin and is less than or equal to. You cannot have greater than or equal to because that would be outside the circle. That would be unbounded. You can't have the dotted line, which would be the less than there. Also, when you have a square here or a rectangle, often it's presented in this style where you're given both the bounds for the x and y, saying they have to occur at the same time. And if any of those don't have an equal sign underneath the inequality, it's not good enough for it to be a closed set. So for now, you're not going to have to really worry about that. It's just kind of an important point that this is what we're going to be dealing with as closed domains. Okay, anyway. Now, here's an analogous thing to what we had before with what we did above, where we have these steps for when you can find the absolute maximum and minimum now based on that extreme value theorem, and some procedures here are given. So first, find the values of f at the critical points of f and d. And so this is something we did in part 1 of this section. So we know how to do that already. But the only difference is we need to check to see if they're actually in our domain. Otherwise, we don't care about them. Step 2, find the extreme values of f on the boundary of D. This is something new. You literally have to take every boundary and check it to see if it's got some extreme values on the boundary. So we'll see that in detail with example. And then finally, step 3, the largest of the values from step 1 and 2 is the absolute maximum value. The smallest of these values is the absolute minimum. So again, similar to the Calc 1 situation, but it's going to be pretty laborious here to find, especially the extreme values on the boundary of D. Alright, before we do this really long example, I'll stop the recording, and then I'll start a new recording for the next one.